Hi guys, we will solve some problems from worksheet 2 and 3. I remarked them with color. As you see, we will solve. Then we will start with the question 6 from the worksheet 2. Okay, I will write the questions though, you don't need to go back that. Okay. This is the problem 6. All right. So we will find in the first part, we will find the limit of f when x is approaching 1 from the left. Okay, so the function is defined by x squared plus 1 when x is less than 1. So you need to compute the limit of this one. When you plug x equals to 1, you will get 2. And we approach 1 from the right. The function is defined by x minus 2 squared. Okay, so you just plug x equals to 1 again and you get 1. You see you don't have the equality. Okay, the right hand side limit is not equal to the left hand side. So in part B, it asks if the limit exists at the point 1. So the answer is no. It does not exist because we don't have the equality. Right, in the part C, you just sketch the graph of f. Okay, for that, you already need to know that the graph of x squared. So we will use that. First, check the boundary. So when x equals to 1, so assume that as you have equality there. If you had equality there, you would get 2 as the image, right? You don't have equality, so you just plug an empty dot. Okay. And now you need to sketch x squared plus 1 for the values of x, which are less than 1. You just sketch you just shift the graph of x squared 1 unit upwards, right? So you have x squared plus 1. Now, when you have equality, when x equals to 1, you have 1. So here you have the dot. And you just sketch the graph of x minus 2 squared, which means you need to shift the graph of x squared 2 units to the right. So you have this one. And you're done. Now in the question 7, you just compute the limit. Okay, you rewrite this as in this form. First, you rewrite the numerator in the parentheses of x squared. You will get 1 over x squared minus 1 over, in the parentheses of x cubed, you have 1 minus 1 over x squared plus 1 over x cubed. Now let's get rid of those x squared and x cubed. You get, if you simplify them, you will get 1 over x, right? So you have this one. Now x is approaching infinity, which means here you will have 0, again 0 and 0, which means you will get minus 1 over x, right? Now x is approaching infinity, so minus 1 over x is approaching 0. And you're done. Let's solve part D2. Now x is approaching infinity, and you have this value. Okay, first you multiply it by its conjugate. And divide it by the same to get the same function as in the beginning. Okay. Now if you multiply them, you will sorry, you will have 9x squared plus x minus 9x squared over the same denominator. So above you have x, and below you have the same denominator. Now let's try to write this in the parentheses of 9x squared. Okay, in the parentheses of 9x squared, you will get 1 plus 1 over 9x plus 3x. We can write this outside of the square root as 3x in the absolute value, of course, right? But you have this value, so x is approaching infinity, which means x's are positive, so you can get rid of those this absolute value, which means you have now this. We can write the denominator in the parentheses of 3x. So you have this now. Now simplify those x's. We have 1 there. So you have 1 over 3 times this parenthesis. Now when x is approaching infinity, you get 0 here. So you have 2 times 3, which gives you 1 over 6. Now question 8. Sorry. We compute this limit now. Okay, we need a recall here. The limit of this function when x is approaching 0 is equal to 1. We will use that. But you don't have, so if we had this value in the denominator, you would separate the limits as you know both exist, then you would be done, right? But you don't have 15 in the denominator, right? You have here 15, but you don't have here. So you need to multiply this function by 15 to get rid of that 15 in the denominator, so you will have equality. Okay, now you can write this 15 outside of the limits. So you have limit of sinus 3x times sinus 5x over 3x times 5x. Now you know both limit exist, so you can separate it. In the parentheses, let's write it. Sinus 3x over 3x and limit of this thing. Now by the recall, you know this is equal to 1, this is equal to 1, so you get 15. Now from worksheet 3, we solve the problem 1, part B. Right, the question is explain why the function is discontinuous at the given point. Okay, then we will sketch the graph. So we say a function is continuous at a point if you have this equality, right? If the image of that function at the given point is equal to its limit, then you say the function is continuous. Now, we need to check the limit of f at the point -2, right? To be able to say it's discontinuous. Because it's already defined by 1 at that point. So that's not the problem. We will have some problem with here, okay? Now let's compute this one first. Let me write directly the definition of the function there. So except -2 at the point -2, the function is defined by this. So you will just directly write it. Okay. Now we approach -2 from the left. So you will have some values. So you have 1 over x plus 2, right? So you will have some values which are really close to 0, right? So you will have infinity. 1 over 0 gives you infinity. Is it plus or minus? You will determine that. You get values which are less than -2. You approach -2 from the left. Let's say -3. So you will have negative values there, right? So you approach 0 from the left, which gives you -infinity. This is enough to say the limit of f does not exist at the point -2, but let's also compute the limit when we approach -2 from the right. Again, the same conditions, the denominator will be really close to 0, but you will have positive values. So you get plus infinity. Okay. So the limit of f at the point -2 does not exist. Hence, the function is discontinuous there. So let's sketch the graph. You need to know the graph of 1 over x to sketch this one. Okay. So the function is defined by 1 over x plus 2 if x is not equal to -2, which means you need to shift the graph of 1 over x to the left 2 units, right? The asymptote here -2. Okay, so you have this. We're not done because the function is defined at the point -2 as 1. So you get the value 1 here. You have a dot there. Sorry. Now you're given the function f defined by this x cubed minus x squared minus 2x over x minus 2, and the point is 2. We will determine if the function f has a removable discontinuity. So before we had the limit infinity, right? One is -infinity and the other one +infinity. So you cannot remove that discontinuity because the limit does not exist. But if the limit exists and if the function is defined, if the limit exists, then you can maybe remove that discontinuity. We will check the limit, that's why. So the problem is here, the point 2. So you need to check the limit at the point 2. Okay, write it in the parentheses of x, you will get this. And you can write this one again as in this form. Now we can get rid of those x minus 2s and get this. Now if you plug x equals to 2, you will get 6. Now the function is not defined there yet, right? When x equals to 2, it's not defined. We have 0 in the denominator, so it's not defined. But it has limits. So if you rewrite the function as in this form, so if x equals to, if x is not equal to 2, let's define the function same. Is it 2x? Sorry. Okay, and if it's equal to 2, so you need to define the function using what? If the function is continuous at the point 2, then you will have, you need to have this one, right? You already compute the limit and get 6, which means you need to define the function using its limit to remove the discontinuity there. Okay, now the function is, the function was already continuous at all points except 2, but now it's also continuous at the point 2, so you're done. All right, for this question, we will determine if the given equation has a solution or not using intermediate value theorem. The interval we will check is 1, 2. Now let f of x be this function, sinus x minus x squared plus x. Okay, so to apply the intermediate value theorem, you need to say that f is continuous on that interval. Okay, so let's say which is continuous on, it is continuous because sinus, x squared, and x are all continuous functions, right? Not only this interval, but also on all real numbers, it's continuous. But we will only look at this interval there. Okay, so you need to say that this equation has a root, which means for some value, sinus x, for some x, you need to have this equality. To apply the intermediate value theorem, you need to find 2 points, A and B, let's say. One of them gets some value under f, which is less than 0, and the other one is positive, okay? If you can find those 2 values, then you will say there is some c between A and B, such that f of c equals to 0. So, okay, so to apply the theorem, you need to find those values. So let's check the boundaries only. Observe. Now, if you check f of 1, you will get sinus 1 minus 1 plus 1, right? We just plug x equals to 1, which gives you sinus 1. And if you use the unit circle, sinus 1 is positive. Okay, so we found already one number. Okay, and if you check f of 2, sine 2 minus 4 plus 2, you will get sinus 2 minus 2, right? Now, sinus, the function sinus x, is in between 1 and minus 1 for any value x, which means you can at most get 1 here. So 1 minus 2 is, again, negative. So this value is always negative. Not always, you already have 1 point, but you get the point. Okay, it's negative. So using the intermediate value theorem, there is some c between 1 and 2 such that f of c equals to 0, which means you found the root to the given equation. Okay, and you're done. Now, is there a number that is exactly one more than its cube? Okay. So first we will write an equation using this definition. So let f of x be what? So is there a number that is exactly one more than its cube? So you need to solve this one, right? So which gives you this. So if there is such x, you will get this equality. Let's define the function using that then. Okay, again, which is, and note that f is continuous on all real numbers. We will need only 2 points on which the function gets negative and positive values separately, right? So observe, I already computed those, found that those points, so I will directly write them. Observe that f of 1 is equal to 1, which is greater than 0, and f of 2, so you will get 8 minus, sorry, 3. Minus 2. We will try. Minus 2. So we'll have minus 8 plus 2 plus 1. You get minus 5, which is less than 0. Thus, by intermediate value theorem again, there is some c now in those values, right? Such that f of c equals to 0. Okay, there is some c comes from here, those values, and this 0 is because of this. So there is such number given the desired condition. Okay, so we're done. We will continue from the problem 5 next week. Okay, see you.